So today we're going to finish our discussion on statistical learning. And it's a very brief introduction, so there is a lot of topics that can be expanded on. But the last lecture, we discussed regression problems, which is trying to come up with a function that explains all of this data, right? So we have a set of xi, yi. By the way, xi and yi both can be multidimensional. Each xi can contain many factors. Like in our last lecture, each xi can contain for one particular product, for example, how much money is spent on TV, how much money is spent on radio and newspaper. So that's a three-dimensional example. And in a lot of realistic cases, x can be a lot higher dimensional, such as millions of dimensions or even billions in some of the machine learning problems with image recognition, which is really looking at a two-dimensional array of data, or even video recognition, which is a three-dimensional array of data, or speech recognition, right? All of these are very high-dimensional axes, and y can also be multidimensional, although it's rarely to have y's that are as high-dimensional as millions, but it may want to grab multiple things from the data. So I mean, you have a lot of axes, you have the corresponding y's. And the regression is to come up to obtain a y hat, y hat of x, is to come up with a function that tries to predict what the corresponding y would be for any given x, such that the difference between yi and y hat of xi is small. So the goal for the regression is not only that this is small for the existing samples, but we also want the difference between the predicted outcome and the actual outcome to be small for some future things that we don't see in the training yet. So for a statistically similar set of xi and yi's, we want this metric to be small. And classification can be thought of as a special example of regression, where the yi's are discrete integers. So regression is basically yi are essentially binary. Okay, binary means is it yes or no? Image classification basically says that for a given image, I want to tell you, does this image contain X or not? Contain a face or not? Right? Or is this face belongs to one person or another person? So this is a binary set of problems. And the metric can be slightly different, right? There are many different ways to determine how good a classification problem is. And for example, logistic regression is one of the ways to classify how good outcome is. While the outcome of a regression problem, it's usually slightly different from just trying to be as similar to the yi as possible. Because one of the reasons for that is if my y hat is actually discrete, either 1 or 0, it doesn't really work if I want to do gradient-based optimization, right? So what's the problem about if I want to construct a y hat that is either 0 or 1? What's the problem about trying to fit a function? Let's say, well, for example, I can use the spirit of linear regression and say, for example, if I follow the spirit of linear regression and I try to predict a yi that is either equal to 0 or 1. And if I follow the spirit, I'm going to say my y hat of x is going to be either 0 or 1 if a particular linear combination, let's say a1 x1 plus a2 x2, etc., plus b is greater than 0 or is less than 0. So what if I come up with this kind of a linear classifier, right? So this is one type of called a linear classifier. Tries to come up with a linear function, and depending on this linear function is greater or less than 0, I'm going to classify my x to be either in one category or another category. So what's the problem about trying to put this in the regression framework and tries to just minimize that function? How would you do that, for example?
It's the problem that depending on your test data, making an infinitesimal change in your classifier function might not change the output.
Yes. So the problem is that the outcome, the loss function, if we define the loss function to be just the summation over I, right? So if I define my loss function to be summation over I goes from 1 to n of that, my loss function is a discontinuous function of my a's and b. If my a and b changes a little bit, infinitesimal amount, there is a high likelihood my objective function is stay exactly the same, right? If my change in the a's and b's are very, very small. Because I have finite number of data points. For every data point, if it is classified as either 0 or 1, which means this one is either greater or less than 0, it's very unlikely this is exactly equal to 0. So by changing the coefficients only a little bit, most likely all the samples that is originally classified as 0 is going to stay 0. Everything that is classified 1 is going to stay 1. But there is a very small chance that even a tiny little bit of perturbation in A's and B's is going to push one of the samples to the other category. So what you're looking at is like a space in the A's and B's. So let's say this is the space in A and B. And if you look at the contour is not continuous. It's in one regions of A and B's, I may get one fixed level. It's a plateau, right? And when A and B changes a little bit, I get another plateau. And in between these two plateaus, there is a cliff. So in some sense, this objective function is not really a very suitable for objective function for gradient-based optimization. Because wherever you take the gradient, almost surely the gradient is going to be exactly 0. And just by changing the A's and B's, even by an infinitesimal amount, most likely you get nothing, and suddenly you have a jump in the objective function. So not very good, not very suitable for gradient-based optimization. So therefore, to make this problem a lot easier for gradient-based optimization, we usually don't try to directly predict, am I going to get a 0 or 1? But rather, I'm going to use this linear function to come up with a probability statement of how likely this particular x is going to belong to 0 or 1. So for example, one of the popular ways to do this is to look at a particular linear function and say the probability that my y ahead of x is equal to 1 is going to be an exponential function of this linear function divided by divided by 1 minus the exponential of the same function. 1 plus, I think, yeah. Right, so this is basically saying a probabilistic statement. And then the loss function is going to be something that relates to this probability. For example, a logarithmic function of such probabilities. So basically, if you classify the probability to be more likely to be the wrong side, you are suffering a higher loss, right? So